Hello everyone. Next packet, chemical composition. Traditionally this is a little bit more challenging for students because there's some math involved which you've never seen before. However, if we think about this math in terms of some common sense ideas, it makes total sense. Okay, so what I'm going to do is introduce the math to you in a kind of a common sense way, and then we'll change it to the chemistry equivalent, if you like. So I like to think of this as supermarket math, okay? And supermarket math is what you do in your head in the supermarket. And all we're going to do is translate that or turn it into the chemistry equivalent, okay? So instead of, in our example, eggs, we'll have atoms or molecules. And instead of pounds, we'll have grams. And instead of the thing called the mole, which is this interesting concept in chemistry, we'll have dozens. Okay? So if you ever get stuck, always come back to this first page and just kind of remind yourself of the concepts, because if you know the concepts, it's honestly not so bad. Okay, so remember, you have the power of the pause button. You can pause at any time. Okay, so here's the concept. We can actually count things by weighing them. Okay, now that's a concept we see, well, we used to see back in the day, back in the 1980s. You'd go to the bank on a Friday afternoon to cash your paycheck, and there'd be some person in front of you with like a whole kind of big tub full of pennies. And you think, oh no, they're going to cash out their pennies and it's going to take forever. And you'd be behind them, and then they'd take the pennies into the back in the bank. And they'd come back literally 2 minutes later, and they'd give them a check for like $125.50 or something. Okay, so how did they count the pennies so quickly? Well, they didn't count them, they weighed them. Okay, so if you know how much a penny weighs, and then you weigh a bag full of pennies, you can figure out how many pennies are in there. And that's the same concept exactly we use in chemistry with this mole concept. We can count things by weighing them. Okay, so let's look at that concept. So, supermarket math. And feel free to kind of just pause and just try this, and then we'll show you the more kind of traditional chain math we've seen before, okay? So a dozen eggs weighs 1.5 pounds, and how many dozen eggs weighs 30 pounds? So it's like like you weighed a carton of eggs and they weighed 1.5 pounds, right? So how many cartons of eggs weigh 30 pounds? Okay, so feel free to pause, give it a shot, okay? And then we'll convert your kind of intuitive math into a kind of more formalized, correct, if you wish, chemistry version. Okay, a chain conversion. All right, so let's look at it. So what we got is a conversion factor, right? Remember, you can convert anything to anything if you have that relationship. In the back of the book, 1 kilogram is 2.205 pounds, stuff like that. We've seen that before. Okay, so a dozen eggs is 1.50 pounds, right? That's the conversion factor, and we're going to use that, remember, as a fraction. Okay, so let's convert it. So there's my starting quantity. I've got 30.0, I'll put LB, pounds of eggs, right? Keep it on top. Times, now remember what goes on the bottom? Hey, the conversion factor, the unit you want to cancel goes on the bottom. I write it as 1.50 pounds and 1 dozen eggs on top. Okay, it doesn't matter how weird the units are, they have to cancel. Okay, later on we'll cancel dozens, but for now, the pounds cancel. Run that through. What do we get? Let's just do the math on the side real quick. Okay. $30 divided by 1.5, 20. 3 sig figs though, right? Don't forget 20.0 dozen, because it didn't cancel, eggs. So you probably MacGyvered that, okay? You probably used your kind of like intuition, kind of supermarket math logic to figure out that, hey, 30 pounds of eggs is 20 dozen eggs. Fair enough. Okay. So that's counting by weighing. Okay. So we got dozens. Later on that'll become moles, which is the chemistry dozen, if you like. Okay. So now the second question, how many single eggs are in 30 pounds of eggs? We need a relationship now between single eggs and something else, and you think you know it, of course. Excuse the phone ringing, I'm at home. 1 dozen eggs equals 12 eggs. All right, that's our conversion factor. Okay, and I could, take this answer and then just do a single chain conversion or single link in the chain conversion, but let's do the whole thing. Okay, let's do the whole thing. I'm going to go from pounds to dozens to number of eggs, right? And it's kind of explained down here. All right, so I'm planning my journey, and I'm just going to put 2 links in the chain. So I'm going to start with exactly what I did up top. 30 pounds of eggs times 1 dozen eggs is 1.5 pounds. So that's exactly what I did before up here. Okay, I'm not going to press equals. I don't want to kind of finish my journey. I want to do this next leg of the journey, which is 1 dozen eggs is 12 eggs. So remember, I can link my conversion factors together. Good to go. Dozens, dozens, pounds, pounds. So 30 times 1 times 12. 30 times 12. Let's just work that out quick. Oh, I forgot. No, mistake there. Okay. 30 divided by 1.5 times 12. My mistake. 30 divided by 1.5 times 12 equals 240 eggs. 366. All right. So there's your kind of overview of how you go from a weight to a number, and then from a number to another number. Okay, and that's exactly the same concept we'll do with chemistry. So we can weigh a number of atoms or molecules on a balance, get a good number in grams, convert that to what we call the chemist's dozen, which is a larger number, but we'll get to it in a second, called the mole. A mole is just a more convenient way of counting things in chemistry, just like the dozen is. A dozen is great for counting things that big, right? So eggs are that big. Don't count them 1 at a time, count them 12 at a time. Donuts too, right? So things of a certain size are easier to count in a dozen. Atoms are real tiny, so we count them a bigger number at a time. We call that the mole, okay? But the concept's the same, okay? It's like the chemist's dozen. We'll talk about the actual number for the mole in a second. All right, so remember, come on back. Always coming back and look at the egg example if you get stuck. All right. So the mole then. The mole is a super important concept in chemistry, okay? It's kind of the central theme of chemistry conversions, okay? Now, my wife is a pharmacist, and she was like valedictorian or whatever in her class, so super smart, right? And I know she's super smart because she chose me as a husband. Now, that's a joke. Okay. She's super smart because she did super good in college. And we chat about things, and pharmacists take chemistry as a prereq. Maybe some of you are thinking about becoming pharmacists, okay? And so I asked her, I said, what was the hardest concept in general chemistry? And she said, the mole. And I go, you're joking, the mole's a super easy concept. It's just a number, right? And she said, yeah, and that's exactly what the guy didn't tell me, okay? So the concept is simple. Don't get confused by this concept of the mole. The number that is the mole is just like the chemist dozen, okay? The mole is like the dozen. It's just a number that represents a bigger number, okay? So if I have things that are the size of eggs, 12 is a great number, okay? A dozen is a number that represents another number, 12, okay? So it's easier to count in dozens, right? When we have tiny, 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 tiny atoms and molecules, we don't count them 12 at a time. That's a silly number to count because they're so tiny. We count them a big old number at a time. So that is the mole constant, okay? A mole is just 6 with 23 zeros behind it. That's a big old number, okay? Things. It can be anything. You can have a mole of anything. It's just counting. You can have a mole of donuts if you want. It's a lot of donuts. 6 with 23 zeros. But hey, that's what it is. But normally when things are tiny, we need a lot of them, okay? So, for example, if I ground up a pencil lead, I'd have about half a mole of carbon atoms in my hand, okay? So, if I want to write that as a real number, 6.02 times 10 to the 23, it's crazy, right? So 6.02 times 10 to the 23, that's a 6 with 23 digits after it. 6, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3 things. Crazy, right? So that's how many things are in a mole of things. Remember, it has to be a crazy number, big crazy number, because atoms and molecules are so tiny. Let's just double check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Yeah, okay. Now, 6.02 times 10 to the 23 is one of those classic numbers in chemistry. Okay, it will be on the data sheet, but it's, you know, you'll get to learn it through use quite simply. Okay, so if I put that in words, what we got? So there's 1,000 million billion. That's a billion right there. Right? 1,000 million billion right there. And then 602,000. So in words, what is a mole? It's 602,000 billion things. That's what it is. All right. So the first person to come up with this concept was Avogadro, a very famous, I think, Italian scientist. Okay. And he modestly named it after himself. So we call it the Avogadro number, number of Avogadro. 1 mole is Avogadro's number. 6 times 10 to the 23 things, whatever you're counting. 602,000 billion things. Now, this is super nerdy, but chemists, you know, celebrate the mole. Okay, if you ever go to a chemistry conference, you'll see stuff like that, right? That is, you can see it on the page in front of you. That's our chemistry mascot. That, yeah, it's a mole. Right, and these things surrounding the mole are, of course, nerds. Okay, now, believe it or not, we have a mole day. The mole has a birthday. Given this right here, can you kind of think when that might be? Okay, so mole day is actually 10/23, okay, so October 23rd, and it runs from 6:02 a.m. to 6:02 p.m. Yeah, we're nerds. We know. Okay, but yeah, we have a mole day. That's a mole day cake. Right. All right. Now back to this number. The mole is a very, very interesting number, right? 602,000 billion. So hey, if the world, the population of the world is 5.7 billion, well, it was back in the day, right? When I did this note packet, it's 7 now, but hey, it's in the billion range, right? So how many moles of people is that in the world? Well, think about that, right? Think about that, yeah. So let's think about it like this. So a billion is here, yeah? So I'm going to do an analogy. I'm not going to solve the problem. I'm going to do the analogy instead, right? Okay. So there's a billion people, okay? There's another billion people, and there's 602,000, okay? So if you think about the billion is really the population of the Earth, right? Population of the Earth. So here's the analogy, okay? So I've got 602,000 people, right? I guess it's there. So that's like the population of the western suburbs. So think about Joliet, Plainfield, Naperville, you know, Wheaton, all those western suburbs, probably around 602,000 people. Fair enough, that knocks out that bit. Okay, so imagine 602,000 people, each holding, to get to here, right, times a billion, each holding the planet Earth in their hand. So think about everybody in the western suburbs holding a planet Earth in their hand. I then have 602,000 times a billion people. Fair enough. That gets me to there. Am I done? No. This is how crazy big the mole is, right? So imagine 602,000 people, that's everyone in the western suburbs, holding the planet Earth in their hand. And I've got to go by a billion again, right? So everybody on the 602,000 planet Earths is holding a planet Earth in their hand. Oh my goodness, that's such a big number, isn't it? So 602,000 planet Earths. Those planet Earths, each of them has a person with a planet Earth in their hand. Okay, so it's 602,000 planet Earths times the planet Earth. It's a crazy, crazy big number, and that's just trying to get it into concept. If you think too much about the size of the number, it's just unbelievable, right? There are literally more atoms in a grain of sand than there are stars in the sky, because atoms are so tiny, so we have to count them this crazy number at a time. Okay, so the mole is super important, and you know, we have to use a big old number. Okay, now, important question. Okay, important question. Why is it such an interesting kind of bizarre number like 6.02? Why not something more simple, just like a 1 with lots of zeros behind it? That would be simpler, wouldn't it? Okay, interesting. Okay, why is the mole this number? Well, it's all about coincidence. Okay, it turns out that if you look in the periodic table, and I don't have a periodic table with me right now, I'll just draw a little symbol. Okay, carbon weighs 12.011. Okay, that means the average carbon atom has 12.011 particles in its nucleus weight, right? It weighs 12.011 AMUs. Remember, a nucleus is composed of neutrons and protons. Each of those things weighs 1 AMU. The average then, you know, for the isotopes of carbon, 12.011 AMUs per atom. Okay, all right. Fair enough. Now, this is where coincidence comes in. We're not going to do the math, and if you take Chemistry 101, we will do this math, but just have to kind of go with it, right? If I change the unit here, okay, and we can convert AMUs to grams. If you want to, try this by yourself, feel free, right? If I had 12.011 grams of carbon, which is the same number, right? Same number. This is the number doing double duty, right? That doesn't equal 1 atom, it equals 1 mole of atoms, which is, remember the constant, only if I define the mole as 6.02 times 10 to the 23 does this coincidence happen. That's why it's a super important number, okay? So this is the mass number from the periodic table, and this works for every single atom in the periodic table. Just look at its mass number box, right? Okay, if you want a periodic table, it's downloadable from my website in the miscellaneous information. Okay, we'll just grab one offline or online, right? Okay, so that's the mass number. It is simultaneously the mass of one atom in AMUs, how many things in the nucleus, or the mass of 1 mole of atoms in grams. So this then allows us to do, and this is super important, it's a trick and a key fact, right? A new conversion factor, right? So we just look at the periodic table and we say, hey, 1 mole of carbon equals that number, 12.01011 grams, okay? So it allows us to make our own conversion factors, which relates how many things, this is the chemist dozen, weigh a certain amount. 30 pounds of eggs, so many dozen. Chemist dozen, so many grams, okay? So this is a new conversion factor which we get straight from the old periodic table. The mass number in grams is a certain number of atoms we call 1 mole. Okay, so that's super important. We'll get some practice with that. Okay, so we now have a couple of super important conversion factors, okay? We can go grams to moles, which we'll practice in a second, just using the mass number from the periodic table. And then, hey, a mole is just a number. It's the Avogadro number, 6 times 10 to the 23. So we can plan our journey now. So before it was pounds to dozens to single eggs. Now it's grams to moles, kind of like the chemist dozen, to number of atoms. Okay. All right. So let's look at the first one. Okay, plan the journey again. The mass of 2 moles of carbon atoms. So we're given 2.0 moles. And feel free to freeze, or pause if you want to try this by yourself. 2 moles of carbon. So 1 mole of carbon, if we look at the previous page, we had that number, 12.011 grams. I can, write that as a conversion factor. That's straight from the periodic table box, okay? So look at the box in the periodic table, it gives you that information. Work it through, moles cancel. Kind of a common sense answer. If you think about it, hey, 1 mole's 12, so 2 moles is 24, right? And that's what we get, 2 times 12.011. Units cancel. You've got to set it up, because on a test, you have to show me the work and the units cancel, okay? You can't just MacGyver it, right? So we get 24.02, we'll say. Okay, actually with sig figs, what is it? 2 sig figs there, we'll just call it 24 grams. Okay. Remember, sig figs are the first quantity always. Okay. So, great place to pause. So feel free to do that and then try the others. Okay, I'll slowly fill them in and we'll look at the answers. Okay, so next one. Moles of carbon in 6 grams. So we're going grams to moles. It's the other direction, right? So 6.0 grams of carbon times grams on the bottom, 12.011 grams is 1 mole. Cancel away. 6 divided by 12.5, right? So that's a nice easy one. Let's just make sure we get all the digits. 6.0 divided by 12.011 equals 0.49995. So 2 sig figs, 0.5 moles. Oh, 50 moles. Makes sense, right? If 1 mole is 12 grams, 6 grams is half of that, so that's half the number of moles. Boom, all right. How that makes sense. Now, next one, whenever you see the actual pure number of atoms, remember you've got to turn moles, which is the chemist does, into actual number of particles, right? So that's that different conversion factor. 1 mole equals 6.02 times 10 to the 23 particles. In this case, atoms, right? So it's this leg of the journey. Previously, we just did these, all right? Oh, come down so you can see that. Right now, we're going to do moles to number of things to moles. Just the first 2 questions we went to and from grams and moles, right? So we're looking at this kind of second kind of phase here. All right. So let's look. Make sure I've got my notes ready to go here. Actually, we can just work it out on the fly, can't we? But we'll do it. So the number of gold atoms in 2 moles. So 2.0 moles gold times, look at that conversion factor, okay? We're going to do moles to number of things. So moles must go on the bottom. 1 mole is 6.02 times 10 to the 23 atoms. Hey, 6 times 10 to the 23 is 1 mole. 2 moles then is 12 times 10 to the 23, or if you do the scientific notation, 1.2 times 10 to the 24 atoms. Do sig figs again. All right. Hopefully that makes sense. Okay, remember it's all about planning the journey. Okay, so read the question. Recognize, hey, I'm going between moles and number of things. I've got to use the Avogadro number as a converter. Okay, in the previous first 2, grams and moles was the way we were going. I've got to use the old periodic table for atoms. Okay, so next thing, number of moles of lead, Pb, in 35.5 grams of lead. So it's moles and grams. Okay, so it's the periodic table. If you look at lead in the periodic table, 1 mole of lead equals, what's my number? 207.2. Okay, so I've got 35.5 grams lead. That's going to be 3 sig figs times grams on the bottom. 207.2 grams is 1 mole. Units cancel. What do I get? 0.171 mole Pb. Fantastic. All right. Okay. Last but not least, we're going to kind of combine those 2 steps. So it says the number of lead atoms in a certain mass. Okay, you can do it by steps. We just did grams to moles, which you get this number. You could take it down here and then just turn it into number of particles, number of atoms. But I want to do it as a straight 2 links in the chain conversion. So let's plan our journey. We got grams, which is given, right? We can only go from grams to moles using the periodic table. That's exactly what we did up there, okay? But I'm not going to press equals. I'm not. I'm going to keep going and turn moles using Avogadro into number of atoms. Okay? So let's run it. So I've got 35.5 grams of lead times this link in the chain. Well, 207.2 grams of lead is 1 mole of lead. That's exactly what we did here, but I'm not pressing equals, right? I'm doing it all at once, okay, which is kind of the preferred way to do it. So I've done this first leg of the journey, grams to moles. Then it's just like doing, like, you know, yards to feet to inches or something, right? There's 2 links in the chain. Finally, 1 mole has to go on the bottom to cancel, right? 1 mole is how many things? 6.02 times 10 to the 23 atoms. run it through, 35.5 divided by 207.2, you get that number, times 6.02 times 10 to the 23, oops, let's write that again, 1.03 times 10 to the 23 atoms. Now remember, if you're working out the number of atoms, it's 23, the number of atoms in a sample, it's always going to be a massive number, a big positive power here. If you happen to get a minus number up here, you mean you got your fraction switched, right? Okay, so remember, it just makes sense that atoms is always a big number, okay? Grams is always in the everyday range, pretty much, right? 35.5 grams is about 1.5 ounces, right? So 1.5 ounces of lead contains a 1 with 23 zeros behind it number of atoms, okay? Or 1/6 of a mole, right? Okay, all right. Hopefully that's good. Okay, we're about half an hour in now, so I'm gonna, pause there. What I'd like you to do, try a bunch of homeworks questions and check the answers in the back of the book, okay? With these simple grams to moles, moles to number of things conversion. So look for questions like this in the homework, answers are in the back. Try them, because this needs to be a solid foundation before we move on to the next stuff. Okay, so just give you a peek on that. What we're going to do in a moment, and this really will help us, we're moving towards solving those questions in our kind of phosphate lab. That's eventually where we're going to go with this stuff, but we need the math background. We're going to start talking about more complex formulas, okay, so molecules, ionic formulas, stuff like that. So we'll extend this to that in the next video. Okay, so I'm going to stop there. Please, put something in the discussion if you've got a question, and really try and get that foundation solid before moving on to this next page, which we'll do next time. Okay.